Hi everybody. Today we're going to be looking at infinite limits. We spent time yesterday looking at one-sided limits. How do we write that coming from the left? How do we write it coming from the right? And I've discussed some limits at infinity a little bit, but not too much in detail. So I want to kind of just clean up some of that conversation today. So I've got a function here that we're going to take a look at. 3 over the absolute value of x minus 2. Now notice I'm going to take the limit as x goes to 2 from the left, the limit as x goes to 2 from the right, and then we'll make a conclusion about the limit as in general as x goes to 2. So what does this look like? Well, we haven't looked at much with that absolute value there. So what I'm thinking here is let's ignore that absolute value for a second. 3 over x minus 2. Hopefully you're able to picture what that looks like. The parent function would be 1 over x. And do you remember what 1 over x looks like? Okay. Now imagine we multiply that by 3. We know they're going to stretch that vertically by 3. This minus 2 is going to move it to the right 2. And I've graphed 3 over x minus 2. It looks like this. Now what's going to happen if we take the absolute value of the denominator, or the whole thing for that matter? Okay. Well, we know absolute value is going to make it positive. So absolute value x minus 2 looks like this. So as we come from the left towards 2, where is this function going? It's going to infinity. As we come from the right, going to 2 from the right, where is it going? It's going to infinity. So that must mean that our limit, it's going to infinity from the left, it's going to infinity from the right, so the limit as x goes to 2 is infinity. Now that means our function is increasing without bound. I've mentioned that in class already. Now here's something, I just want to make sure that this is super clear. Okay. A limit equaling infinity, so I said this limit equals infinity, does not mean that that limit exists. Okay, I've mentioned this already, but I'm trying to clean this up. Are we approaching a number? The same number from the left and right? No, we're going to infinity. Infinity itself is not a number, it's kind of the concept. Okay, so a limit equaling infinity does not mean that the limit exists. What we are saying is that the limit fails to exist by denoting the unbounded behavior. So this limit does not exist, but we're giving a little bit more information than just saying does not exist. We're saying, you know what? It doesn't exist because it's going to infinity. Now, we see this happen because we have what here? We have a vertical asymptote. So we're going to spend a little bit of time today talking about just reviewing, hey, how do we find these vertical asymptotes? All right, so let's evaluate some limits here. We have the function 1 over x minus 3. Okay, what is the limit as x goes to 3? This is a little bit simpler version. We've got 1 over, no absolute value down here, x minus 3 looks like this. Limit as x goes to 3. Well, we've got a vertical asymptote at 3. As we come from the left, we're going to negative infinity. As we come from the right, we're going to infinity. So this limit does not exist. This one's going to negative infinity. This one's going to positive infinity. Okay. Now, the previous example, the limit didn't exist, but we said the limit was equal to infinity to show that it was going to the same place. It was going up forever and ever and ever. Okay. This one, we can't say that because one's going to negative infinity, one's going to positive infinity. So we're going to say that this does not exist. Now, what happens to that function if I square it? Okay, thinking what squaring does to numbers. It does make the numbers bigger, but it also will take any negative and make it positive. So what would we say on this one? As we come from the left, we're going to infinity. As we come from the right, we're going to infinity. So we will say that the limit as x goes to 3 of 1 over x minus 3 squared equals infinity. Again, that limit doesn't exist, but we are saying, describing what's going on here. What happens if I put a negative there? Well, we know what happens to graphs when we put a negative in front. Okay, reflects it over the x-axis. So what would we say on this one? Negative infinity. All right. Okay. Let's just remind ourselves, quick review on how we find the vertical asymptotes. Each of the problems so far, I just graphed it, but let's just have a quick review here. A function f of x over g of x, okay, has a vertical asymptote at x equals c when, well, what do we have to be careful about? Dividing by 0, right? When g of c equals 0. But we have to recall the difference between a vertical asymptote and a hole. Remember, holes happen when we have 0 divided by 0, when it's indeterminate. We have vertical asymptotes when it's undefined. So we're going to say that as a vertical asymptote at c, when g of c equals 0, but f of c does not equal 0. We're looking for a number other than 0 on the top. Some number other than 0 on the top. Okay. This is indeterminate when we have holes, and this is undefined. So, determine the vertical asymptotes here. Well, where is that denominator equal to 0? When x equals 1. Let's do a quick check. F of 1 is what? 1 over 0. That's undefined. Vertical asymptote. X squared plus 2x plus 3 over x squared minus 1. Where does that denominator equal to 0? Well, I'll factor the top and the bottom here. That's x plus 3, x minus 1, over x plus 1, x minus 1. Where is the denominator equal to 0? At negative 1 and at 1. But we have to double check. Okay, make sure it's not a hole. It is actually a vertical asymptote. When I put in negative 1, what do I end up with here? 2 times negative 2, that's negative 4, over 0 times negative 2, that's 0. This is a vertical asymptote. But when I put in 1, I end up with 0 over 0. This one's the hole. Vertical asymptote is negative 1. X squared over x minus 4. Where's that denominator equal to 0? At 4. Let's check it. That would be 16 over 0. This is a vertical asymptote. X squared plus 2x minus 8 over x squared minus 4. X plus 4, x minus 2 on the top. X plus 2, x minus 2 on the bottom. So the denominator is equal to 0 at negative 2 or at 2. If we check negative 2, that would be 2 times negative 4, negative 8 over 0. That's a vertical asymptote. But when I put in 2, I end up with 0 over 0. That's the hole. Remember that holes happen when our factors cancel out. It's a reminder there. We saw that on this one as well. The x minus 1's cancel. That's why x equals 1 ends up being a hole there. 0 over 0. All right, last thing that we're going to look at here in this video is finding some limits. Just thinking about the different properties that we have. Think about what we've learned so far today about infinite limits. So what's the limit as x goes to 0 of 1 over x squared? Well, x equals 0, we should recognize from our conversation, is a vertical asymptote. So as we go to 0, okay, this is going to, well, let's just double check, 1 over x squared, that's going to be positive numbers. Okay, to the left of 0 and to the right of 0, that's going to be positive. This is one that's going up to infinity, so we would say this is infinity. Now, what if I take the limit as x goes to 0 of 1 plus 1 over x squared? Okay. Well, when we talked about limits the other day, we looked at properties. And if I'm taking the limit of a sum of two different functions, I can take the limit of each of those functions individually. What's the limit as x goes to 0 of 1? 1. What's the limit as x goes to 0 of 1 over x squared? We said that's infinity. So if this is going to 1 and that's going to infinity and we're adding those together, where is this function going to go? That's going to go to infinity. Thinking about transformations of graphs, all we did is take this graph, added 1, that slides it up 1. That doesn't change the fact that that's going to infinity. All right, here, limit as x goes to 0 of x plus 2 over 1 over x squared. Okay, if I'm taking the limit of a quotient, I can take the limit of the top over the limit of the bottom. Now, the limit of the top, as x goes to 0 of x plus 2, where is this function going as x goes to 0? That's just a line. Nice continuous function, well behaved. We can put in 0. The top is going to 2. Now the bottom function, we already know, is going to infinity. So if the top is approaching 2 and the bottom is approaching infinity, what is this function doing? So the top is approaching just a finite number of 2, but the bottom is getting bigger and bigger and bigger and bigger and bigger. Okay. What happens to a fraction as the denominator gets bigger and bigger and bigger and bigger? That fraction is going towards 0. Okay. 2 over 10, 2 over 100, 2 over 1,000. Okay, isn't this fraction getting smaller? Isn't that fraction approaching 0? Okay. Now, how about this one? I've just taken the reciprocal of this. The limit of the numerator, that's going towards infinity. Limit of the denominator is 2. What happens to a fraction if the numerator is increasing without bound? That's getting bigger and bigger and bigger and bigger. But this is just approaching 2. Well, what happens if I flip all those? 10 over 2, 100 over 2, 1,000 over 2. What's happening to this number? They're just getting bigger. No signs of stopping either. This is going to increase without bound. This limit is infinity. So again, just want to point out, because we say that the limit equals infinity does not mean that it exists. It just means, we're denoting that unbounded behavior and being a little bit more specific than does not exist. Hopefully what we looked at there was good. Hopefully our review of where we find vertical asymptotes and what's the difference between an asymptote and a whole is helpful for you as well. With that, I'll see you later. Thanks for tuning in.